electrical energy and power. Electrical energy and power. Let us consider a conductor like this. So let us suppose this is a conductor. At one end say A, the other end is say some B. Now the potential at A, let us call this as VA. The potential at B is VB. If a steady current flows through this from A to B, so let us suppose I be the current that flowing from A to B. So during a small time interval delta t, the charge that has flown from A to B, so let us suppose say Q is the charge. So a charge has flown from A to B during a time delta t. So therefore we can say Q is nothing but I into delta t. Now the potential of B is actually less than A. Therefore we know that charges flow from high potential to low potential. So there is a change in potential energy of the charge that has flown from A to B. Therefore, if I want to calculate the change in potential energy, so I will write like this. So the potential energy at B minus potential energy at B. That is the potential energy of the charge at a final position minus potential charge at initial position. So here we know how to write this. VB, suppose the potential, minus VA. So final VB minus VA into this the charge that has flown. So we can say that is equal to VQ. But actually the potential at B is less than at A. So we know that VB is less than VA. So we can put a negative sign here because the charges are moving from higher potential to lower potential, means its potential energy decreases. So it lost say some this much of energy. So this energy, that is change in potential energy, that is equal to minus V into, in the place of Q I can write I into delta T. So I into delta T. Suppose in the conductor, if the charge carriers are moving without any collision, the decrease in kinetic energy must be equal to increase in kinetic energy. Decrease in potential energy must be equal to increase in kinetic energy. So this is in accordance with law of conservation of energy. So therefore this because change in kinetic energy plus change in potential energy must be 0. Therefore your delta K must be equal to minus delta U. That is according to law of conservation of energy. Suppose if there are no collisions, the gain in kinetic energy must be equal to decrease in potential energy. Hence we can write like this. So minus of minus plus, therefore V into I into delta T. So that is the work done on the charge carriers is seen as increase in kinetic energy. Therefore we can write like this: the work done by the electric field in pushing the charges from A to B, that is given as this, that is the gain in kinetic energy. But actually you know that the electrons will be drifting through the conductor, colliding with the ions and atoms. So what happens? Their kinetic energy is transferred to this ions. So they vibrate more violently. So already there will be oscillating motion. The atoms in the solid will be oscillating or vibrating about their mean position. Due to the collision with these charge carriers, due to transfer of this kinetic energy, they oscillate or vibrate more violently. That means their kinetic energy increases. So this is seen in the form of heating of the conductor. So that we know in first year we studied that kinetic energy is responsible for the heat energy of a system or a body. So whenever the change in temperature is a function of kinetic energy. We have already studied that in kinetic theory of gases chapter. Therefore, here we can say that so the kinetic energy of the ions or atoms increases, and that is seen as heat generated across the conductor. So therefore, if I talk about power is rate of doing work. So therefore, that is equal to VI. And hence, we can write power as P is equal to VI. Or from Ohm's law, we know that V is equal to IR. Therefore, if you substitute here for V, the power formula becomes power is equal to I square R. I can write. So in the place of I, if you substitute I is equal to V by R, here you put V by R, V will be V square. So therefore it will be V square by R. So we can use either this formula or this formula to calibrate power. So this formula has very much importance in power transmission. So we will discuss power transmission from generating stations to the houses, how it happens and why the power is transmitted at very high voltages. We know that, or you might have seen in substations nearby your towns or villages, they are marked as 33 kV or 11 kV or so. So from the generator at the power generating stations like in Srisailam or Nagasagar, where there is hydroelectric power is being generated, or in Ramagundam or Ibrahimapatnam near Vijayawada, thermal power is used to produce electrical energy or electrical power. So the power generated is raised to a very high volts of the order of 66 kilovolts or more than that. And using thick cables and very tall pylons, the power is transmitted, that is electrical energy is transmitted to substations where it is reduced to say some 33 kilovolts or to 11 kilovolts. And this is supplied to the factories or industries where they use high voltage current. Now, if the substations are sending power to the houses, they will send it to a transformer. So there, this 11 kV is reduced to say some 400 kilovolts or so, and is sent to the transformer near our houses, where it is reduced to 240 or 220 volts in India. So it is reduced to 220 volts with the help of transformers. To increase the voltage or to decrease the voltage, we use transformers. So you might have seen a transformer. So the transformer near our houses reduces the voltage of the current coming from the substations. It may be of some hundreds of volts and it is reduced to 220 volts and is given to our houses at this voltage. So, why the voltage is raised to a very high degree and transmitted through the cables, that can be explained with the help of this formula. Suppose you have to supply energy to a device of power P with a rated voltage V. if you observe, the electrical devices are printed with wattage and voltage. So if you see the incandescent bulb, there you might have seen 60 volts or say some 60 watt bulb, 60 watt bulb that can operate at 220 volts. So the voltage and wattage are printed on the given on the devices itself. Suppose you have a device with a power P and operating voltage or working voltage V. Suppose from the relation P is equal to VI. So that is the power formula. Now it has a resistance of say some R, and hence from that formula we can write like this: power is equal to V square by R. So that can be used like this, or we can say that okay, P is equal to, or I is equal to, the current required is P by V. So let us say. Now you are transmitting the current through very long cables. Even though they are made up of good conductors, they have certain resistance. Let us suppose the cable of several hundred kilometers has a resistance of RC. Now the current through the conductor is same. The same current is to pass through it. So let us suppose the current of I is passing through that. Then due to resistance of the cable, there will be a loss of power. So therefore the power lost in the cables is given by, in terms of RC and I, we know that is I square RC. The power dissipated, that is used in heating the cable, is given by this formula as I shown there. But I is nothing but P by V. So therefore I can write like this: P square by V square into RC. So this is the relation we want. For if the power loss or the power wasted in the transmission cables is proportional to the cable resistance and inversely proportional to the square of the voltage. Therefore, instead of this value, this is more important because it has a square term. Therefore, if you transmit the power at high voltage, since it is in the denominator, the PC value will be lesser. So as you increase V, PC decreases. Therefore, power, because the cable loss is inversely proportional to the V square for constant RC, and the device power is constant. Therefore, supplying a power, at high voltage is more advantageous. It has more advantage in reducing the loss of electrical energy. That's why the power the voltage of the power generated station is raised to a very high value and transmitted through very long cables, and later it is reduced and transmitted to our houses and factories. So that is about power transmission, and that is about electrical energy and electrical power. Now we will talk about combination of resistors. Already in 10th class you might have studied about how resistors can be connected in series and parallel. Just we revise the same concept now. So series and parallel combination of resistors. First we will talk about series. So you know a resistor is represented by something like a split breaker symbol. Suppose if two resistors, say R1 and say this is R2, are connected between the 2 points like this. So one end of resistor is connected to one end of another resistor such that current has only one path. The current can travel only in one path or through the resistors, or same current passes through the resistors. Such a connection in which current has only one path to travel through the resistors is known as a series connection. In that case, suppose here we say some point C. So the potential difference across these two, so let us say V1 across these two, let us say V2, but the current passing through them is same. Therefore, I want to know the potential difference between A and B. So I have to add the potential differences. It is just nothing but that. Potential is nothing but work done in moving a unit charge across a resistor or across a conductor. So, to push a unit charge, how much work you have to done in an electric field, or to move a charge from one point to another point in an electric field, how much work is done. So that is called as potential difference. Therefore, between these 2 points or across the distance R1, potential difference is this. Across this, potential difference is V. So total potential difference between A and B is this much. And therefore, we can write like this. From the formula Ohm's law, V is equal to IR. VAB can be written as I into resistance, we call it as effective resistance across AB, that is equal to V1 from the same formula, I into R1 plus I into R2. Since I is common on both sides, we can write R effective is equal to R1 plus R2. So that is the in series connection, the effective resistance is sum of the resistors in the connection. So for any number of, in general we can write like this, for any number of resistors in series, so you can find out by taking the sum. Okay, and one important point is, in series connection of resistors, the current passing through the resistors is same, but potential difference across different resistors are different. So that is simple thing. Similarly, we will talk about the parallel connection. Second one is parallel. In parallel connection, the resistors are joined like this. So between 2 points, suppose these are the 2 resistors. One end of the resistors are connected to one point, other end of the resistors are connected to another point. So here, let us suppose if I current passes through, we call this as junction. The current branches out and comes out. So let us suppose through R1 the current is I1, through R2 the current is I2. So therefore, at any junction we can easily say that total current is sum of the currents. So since charges cannot reside anywhere here, so they have to move, so they don't get stored up there. Therefore, whatever current going towards this junction is equal to what the currents coming at this junction. So they are meeting. Hence I can write like this. So total current I is given by I1 plus I2. And from our Ohm's law formula again, so that is for I is equal to, we know I is equal to V by R. So from Ohm's law, since A and B are common to R1 and R2, potential difference is same. So let us say the potential difference is same across both the resistors. So VAB, or let us call that as V. So from this formula, V by effective resistance is equal to, I1 can be written as V by R1, this can be written as V by R2. So here the V is common, hence it gets cancelled. the reciprocal of effective resistance is sum of the reciprocals of resistors in parallel connection. For any number of resistors, you can use the same formula. So if there are n number of resistors in parallel, you can write like this, and so on, like this. So in parallel connection, the effective resistance reciprocal value is given by the sum of the reciprocals of resistors in parallel combination. Here, the potential difference across all the resistors are same, but the currents through the resistors are different. Now, one more point. In series connection of resistors, the effective resistance is greater than the individual resistors in series, whereas in parallel combination, the effective resistance is less than the least resistor in the parallel combination. We can explain why the resistance is more, why the resistance is there here. So it is nothing but as if the length of the conductor is increasing. You know, R is proportional to L by A. For same area of cross section, we can assume that as the length of the conductors are increasing, R is increasing. Like that we can consider. And in this case, as if the resistors are kept one over the other, so area of cross section is increasing. Suppose they have the same L value. So as the area of cross section is increasing, the resistance inversely depends on the area. Hence, the effective resistance should decrease. So therefore, we can think of this formula and apply why in parallel combination effective resistance decreases, why in series combination resistance increases. So that is about resistors connected in series and connected in parallel.